Hello, I'm Jong-moon from South Korea. I'm a PhD student in the Kaesong Graduate School advised by Edward Choi. I'll introduce our recent work, which was accepted in this BMVC conference. The title of our work is Correlation between Alignment Uniformity and Performance of Dense Contrastive Representations. The motivation of our work is to start from the recent unsupervised contrastive learning approach. Instance-level contrastive learning with a single object dataset has been shown to be highly effective for learning visual representation in a self-supervised manner. Although instance-level contrastive features have been successful in improving image classification performance, it has been observed that they do not enjoy the same transferability to dense prediction tasks. To understand the semantic structures and behavior of this method, a few recent studies analyzed the latent space from the perspective of uniformity and alignment. Intuitively, it is effective to analyze from these two perspectives, since features of all classes can be linearly separated from the rest of the feature space if they are sufficiently well clustered. Since the receptive field of global averaged pooled features typically extends to the entire image, the pooled features are reflected by the background information, making it difficult to localize. To overcome this gap, recent studies have developed a dense contrastive learning with multi-object dataset using dense features to explicitly consider spatial information over regions and achieve the comparable or better results compared to supervised image pre-training. Despite such initial success, this was back at an important yet unexplored question. How different are the dense level features compared to the instance level features? In this work, we investigate the dense feature representation in terms of alignment and uniformity inspired by the pioneering work. We extend the conventional contrastive loss to construct a more principled dense level contrastive loss, and introduce a new scalar metric to succinctly report the alignment and uniformity behavior of latent features. The contribution of our work can be summarized as three things. First, we empirically show that the alignment and uniformity property in dense features is correlated with both instance level and dense level downstream task performance. Second, we found that instance level contrastive features pre-trained on multi-object dataset can perform well on object detection, and dense contrastive features pre-trained on single object dataset can perform well on linear evaluation, both cases following the alignment uniformity principle. We investigate diverse strategies for selecting positive dense feature pairs during dense contrastive learning and find that a simple index-wise matching performs well with appropriate image augmentation. Our method is inspired by the recent work that aimed to understand instance-level contrastive learning with inferential loss. The general form of instance-level contrastive loss is defined as follows, where n denotes the number of randomly drawn instances, b is the mini-batch, gi and gj are the positive pair of instance-level latent vectors projected into a hypersphere, lambda is the temperature. This equation can be rewritten as follows by applying logarithmic rules as like this. We confirm that the contrastive loss indeed consists of two objectives. One issue in DenseL is finding the appropriate features to form positive pairs. The key to matching dense feature is that positive pairs must share information while negative pairs must repair each other. We address this issue with a spatially grounded index-wise dense feature matching based on the assumption that dense features of an instance and sample data points are IID. Our motivation for doing index-wise matching is to fairly compare the behavior of DenseL on multiple criteria. Contrastive learning can learn feature representation when the distance between positive samples is shorter than between negative samples. Also, this approach admits that negative samples contain noisy samples of the positive classes, and these noises are negligible when the strong negative samples are large enough. In this context, our simple approach is also reasonable when effective in learning feature representation. In order to analyze the behavior of dense features in CL, we first formalized the density objective, a natural extension of instance level CL to the dense level. Following the principle of instance level contrastive learning, we assume that all dense features in a single image are IID. Density contrastive can be defined as follows. This equation also can be rewritten as follows by applying logarithmic rules, where we again observe that density consists of alignment and distribution objectives. Therefore, dense features will asymptotically achieve the alignment and uniformity properties similar to the instance level CL. We control these properties more directly. For the uniformity loss, we utilize the Gaussian potential kernel G and the log of the dense average pairwise Gaussian potential. Perfect optimization of both properties is difficult to attain from a finite number of the data points, but can be approximated when the data points are sufficiently large. Therefore, we use LA and LU as the objective function of the pre-training phase and observe whether the two properties are correlated with the downstream task for a wide range of scenarios. If the pre-trained model shows a sufficiently optimized with a low loss and achieves high performance on each downstream task, then the correlation is negative. We investigate the performance of linear evaluation and alignment uniformity properties on the STL10 dataset using a global average pooling feature. As you can see on Figure 2a and Table 1, the overall trend showed that the linear evaluation performance improved for the optimized alignment uniformity property in both instance and dense level CL. And all experiments showed a negative correlation, and two pre-training schemes achieved similar performance. These results show that the dense CL pre-trained on a single object dataset has the ability to linearly separate by capturing the global information. To investigate the dense level evaluation, we analyze the correlation between the alignment and uniformity of dense features on the STL10 dataset, and we will see object detection performance. In this experiment, we can observe that the overall trend of the object detection performance is also correlated with the alignment uniformity property in both instance and dense level CL, and show the similar performance. The instance level and dense level CL using a single object shows a negative correlation between the alignment uniformity and the object detection ability. We conduct instance level evaluation on COCO pre-trained models. The alignment uniformity properties were measured using the global average fold feature on the COCO test set while performing linear evaluation using the STL10 dataset. As shown in Figure 3a and Table 2, the trends of instance level CL showed the strong negative correlations. However, for the pre-training schemes with dense CL, the results showed an irregular pattern depending on the uniformity, showing a weak correlation. Also, COCO pre-training showed that inferior to STL pre-training in linear evaluation in instance level and dense CL. We perform an object detection task to investigate whether such a performance gap occurs in dense prediction tasks. To evaluate the dense features on COCO pre-trained model, we analyze the correlation between alignment uniformity dense features of COCO test set and VOC object detection performance. As seen from Figure 3b, all experiments showed that how high performance as the alignment uniformity metric decreased. Also, the instance level and dense CL showed high performance. From these results, pre-training schemes with instance level or dense contrastive using multiple object perform well in dense prediction tasks, despite the complexity of rich symmetric information. Our assumption of feature matching by the index for positive pairs is that all features are IID. But two views from the same image should contain shared information. To investigate this assumption in the dataset, we analyze using non-overlapping image settings for confusing positive samples on STL10 and COCO dataset. In Table 3, the STL10 pre-training results of the linear evaluation and object detection achieved high performance on a single object dataset and showed a strong negative correlation. However, the pre-training with confusing positive samples on multi-object dataset showed inferior results in linear evaluation and object detection tasks. In particular, object detection showed a similar performance with random initialization result in the object detection task and showed a positive correlation. Therefore, the positive pairing plays a crucial role in dense contrastive learning so that positive pairs can share mutually agreeable information in multi-object datasets. In this work, we mainly analyzed the theoretical ideas of dense CL using a standard CNN and straightforward feature matching scheme rather than propose a new complex method. By extending existing instance level CL analysis method to dense level, we observed the correlation between alignment uniformity property of dense features and downstream tasks with a newly proposed Scala matrix. Also, we discovered a core principle in constructing a positive pair of dense features and empirically proved its validity with a simple index-wise matching. In extensive experiments, we find that regardless of pre-training schemes, pre-training on single-object data sets showed the ability to linearly separate by the capturing the global information and perform well on object detection tasks on multiple object data sets. Furthermore, our work can be potentially used to compare the performance of different CL schemes by evaluating alignment and uniformity properties of instance and dense level features before performing downstream tasks. The novelty of our work lies in carefully designed experiments and evaluation metric, allowing a reliable conversion from the expected to confirmed. We believe that the researchers can now safely rely on our findings and move on to developing more principled CL methods in the future, while treating our methods as a minimum baselines. This is the end of my presentation, and thank you for your attention.